Hello and welcome back. So we were discussing about the application of lasers in chemistry, laser induced photochemical processes, and we were particularly talking about unimolecular laser induced reactions. So I will start with another example. In the last class we stopped where we discussed about the conversion of this 7-dehydrocholesterol to the pre-vitamin D3 and its conversion to finally D3, and these are the chemical structures of those three molecules. Now, most unimolecular laser induced reactions involved multiphoton infrared dissociation. Let us get some good examples. So, one good example is the elimination reaction involving esters, which proceeds as shown in this scheme. So, you have an ester, so it is like C double bond O and O R, R is an alkyl group, and this is the transition state. So, when you excite this molecule by laser of particular wavelength, it goes to the excited state, and the excited state structure is something like this, which is a transition state, or here I will call it like a intermediate. And here what happens, this essentially this part is going here, right. So, this oxygen lone pair, it can actually attack here, and you get something like this structure. And in the next step, what happens, this hydrogen is abstracted by this OH, then this bond is broken, right, and this bond is also broken, and this becomes C double bond O, and this is what we get an acid and we get an alkene. So, this is an elimination reaction, and this is an example of an unimolecular reaction induced by laser. And not only that, this particular reaction is achieved using multiphoton excitation, and the yield and selectivity of this particular product using the multiphoton excitation is really high, and that is why one need to really care about the laser induced chemical reactions, and this is of tremendous importance in industry as well. Now, such reactions can be very effectively induced by a laser frequency of around 1050 centimeter inverse, which produces excitation of the stretching mode of OCH2 bond. So, CO stretching, that is specifically this bond I am talking about. So, it excites this one. So, if you remember this potential energy diagram, so essentially you are having this multiphoton transition and then ultimately go here. So, what it does, it affects the vibration of the CO bond, and after some time the CO bond goes so further that they are no longer within the same molecule, and that is what exactly is this reaction. You get C double bond O instead of this alkyl group attached to this oxygen. Okay, and that is what is the whole mechanism. Now, there are certain cases, especially in comparatively small molecules, where irradiation at different laser frequencies genuinely results in different products. So, which is you can understand how important that can be. Cyclopropane, which is like this. So, this cyclopropane, where it is found that multiphoton excitation at around 3000 centimeter inverse corresponding to the CH stretching frequency result in isomerization to propene. So, if you excite it by photon, where nu is approximately 3000 centimeter inverse, this will lead to the stretching of CH bond, and because of that you end up getting propene, which is CH3 C double bond C, this. Okay. So, now that is for this 3000 centimeter inverse, but if you irradiate at around 1000 centimeter inverse corresponding to the CH2 wagging. Okay. So, we were talking about the CH stretching. Now, if you talk about the CH2 moiety, so you have essentially C and H, right. So, this one, this movement is known as wagging, okay, and that produces both isomerization as well as fragmentation in roughly equal amount. So, some amount you will get this propene, which is isomer. Also you can break into products like methane and ethylene stuff. Okay. Next we will look into the laser sensitized reaction, which is really important not only in chemistry but also in medical sciences. So, this laser sensitized reaction, it involves the sensitization of reactions by the excitation of a species which does not itself undergo the chemical change. So, this can be regarded as a form of laser assisted homogeneous catalysis. Okay. Now, this kind of reaction generally proceeds as a result of the collisional transfer of vibrational energy, often referred to as vibrational transfer, from the molecules of the laser excited species, that is the sensitizer, to the reactant molecules. So, if I put it in a nutshell, then what it is, then I have some molecule which takes up the light energy from laser and then gets excited. Now, this guy does not do anything other than transferring this energy to another molecule, which is the real reactant, and then it proceeds toward the overall reaction. So, this guy again comes back and then again do the job, which is pretty much similar to a catalyst, the role of a catalyst that is played in a homogeneous catalytic reactions. And the advantage of this laser sensitization is it will be clear if the reactants do not themselves strongly absorb in the emission region of the particular laser. This is quite easy to understand. So, it is the photosensitizer which will absorb, not the reactants. So, reactants are kind of transparent to this laser wavelength that is being used. So, if you do not use that light, no reaction will happen. Once you use that particular laser frequency, this photosensitizer will absorb, go to the excited state, transfer its energy, and the reaction will proceed. If you can choose a strongly absorbing sensitizer to initiate the reaction, the rate of the reaction induced by laser stimulation can be greatly increased. Now, a couple of sensitizers which are widely used is sulfur hexafluoride or SF6 and silicon tetrafluoride or SiF4. In the presence of this silicon tetrafluoride, various types of sensitized gas phase reactions have been observed. One example is here. You have an alene molecule here, and this alene is isomerized into this propyne, okay, or methyl acetylene. And then if you take this chlorofluoromethane and you excite it, you excite the sensitizer SiF4 by a suitable laser light, then you get this reaction where two molecules of HCl comes out from this reaction, and this is known as a condensation reaction in chemistry. And the next two examples are essentially the example of Retro-Diels-Alder reaction. So, you essentially excite SiF4 and SiF4 transfers its energy to this molecule, which then breaks apart into two molecules, one is diene and another is dienophile, as they call it in chemistry. And many such reactions which are normally carried out at higher temperature. So, this retro-Diels-Alder reaction that I talked about, the opposite to that is Diels-Alder reactions. You require a lot of heat in order to get this reaction going. So, this kind of reaction which normally carried out at high temperatures or with using a laser heating process. When you use laser, it produces chemically cleaner products if they are induced by a sensitizer which absorbs the laser light, because you really do not produce heat due to this in any way during this reaction sensitized by say SiF4. And such reactions may also be strongly influenced by the choice of sensitizer, of course, and the pressure ratio of sensitizer to reagent. So, these are two important things that people should keep in mind while proceeding for a photochemical reaction initiated by the laser light absorption of a sensitizer. Because the reactants in a sensitized reaction do not need to possess absorption band in any particular infrared region, then with a good sensitizer like SiF4, the range of gas phase reaction in which can be laser induced is almost limitless. That is the biggest advantage, because when I use a photosensitizer, and if I have a good photosensitizer, then I really do not care about whether my reactants are going to absorb in the particular laser wavelength or not. This is really a big advantage, okay, and which is provided by the existence of a photosensitizer like silicon tetrafluoride or sulfur hexafluoride. And another related topic is the laser catalyzed reaction. This is a term which is a very definite misnomer. It does not need to be mistaken, but it is applied to a reaction in which a catalyst is itself produced in laser chemistry. One example, the laser pyrolysis of OCS using 248 nanometer radiation from a krypton fluoride laser produces ground state S2 molecules, which can catalyze the isomerization of cis-2-butene to trans-2-butene with an effective quantum yield of about 200, which is a great amount. So, here you can see that the catalyst itself can be produced by a chemical reaction. Okay. So, it should not be confused with a direct catalytic reaction, but actually the catalyst is being produced by the laser excitation, and then that catalyst helps one reaction to proceed. This getting this S2 molecule otherwise is very difficult. Okay. So, having discussed about those laser induced chemistries, let us now draw our attention into another domain where laser is used to probe chemical reaction or very fast processes going on due to a chemical reaction. So, we will be talking about ultra-fast chemical reaction dynamics with ultra short pulse lasers. Now, first let us consider a chemical transformation which is given here on the screen. Is the methyl iodide reacting with sodium and ultimately forming CH3 radical and sodium iodide. Now, I have two molecules, and from there I generate another two molecules. Okay. So, the initial reactants and the final products, their number are 4 and none of them are identical, right. So, then there must be something happening, some intermediate is being formed, or the transition state is being formed. How does that transition state look like? How the transition state is evolved, and from transition state how the product is evolved, that one needs to understand. This is of a fundamental interest, and this is tremendously important if we really want to understand the chemistry really well. Now, in any chemical reaction, the motion of the electrons and nuclei of atoms determine how the molecules interact, as I was saying, and those interactions in turn create the forces that govern the reaction's dynamics. Now, our aim is to determine how these molecular motions change during the critical transition phase from reaction to product, and we can understand how new chemical bonds are formed and old ones get broken. So, if this is the aim, then we are essentially looking into something like this. So, here you have some snapshots which are taken from some simulation result. So, if you have a hydrogen iodide reacting with a carbon dioxide, then how it reacts? So, the molecules, they orient themselves in a particular configuration, and then the approach of two atoms toward each other happens, and then detachment of certain part and formation of the new bond, and that is what is the final product. So, here like you can see this hydrogen iodide, that bond distance is altered and it goes and attacks this CO2 molecule, and then CO2 orients itself in such a way that this hydrogen is it attacks the oxygen molecule of the carbon, and then it takes away the oxygen with it, and then carbon is left with only one oxygen. So, now this is from the simulation. Now, this is a bimolecular process. Now, how do I really visualize this one? That is something which we would like to know, right. So, our question is, how can one study the transition state in real time? Okay. Now, the answer to this question is that we need ultrafast probe and ultrafast detection technique, and this is the work which got Professor Ahmedzell the Nobel Prize in 1999 in chemistry for his studies of transition states of chemical reactions using femtosecond spectroscopy. So, he used ultra short pulse laser to do spectroscopy to find out the ultra fast processes happening in chemistry, that is how the transition state evolves. And just for your information, this is the first paper that he published in this direction. Some more. Now, on your screen you can see there is a video of a horse trotting. So, while the horse executes this trotting motion, lot of questions was there, like is there any moment when all the four hooves of the horse are above ground? A lot of debate was going on, and people did not know the answer, because there were no so fast camera that could give you the answer. So, this answer was given by at some point of time by doing photography at a real fast scale, and in one of the snapshot it was seen that yes, literally all the four hooves lie above the ground at one particular time. So, this answer could be given because there was a technique developed which could take snapshots of any object in moving condition or in motion in a much faster rate. Okay. So, this is something known as stroboscopy. So, you here the person who actually resolved this problem was name is Bridge, and he took this photograph. So, you can see that there are individual photographs taken during the hot trotting, and they were taken so fast at that type point of time, and if you look into each individual frames, you will see at one particular frame all the 4 hoops are above the ground level. Okay. So, like if you look into this particular one, you can see all the legs are above the ground. Now, similarly, if you take an apple and just leave it, it will fall. Now, how actually it is falling? Okay, at different falling stage, how it is oriented. If you want to know that, you really need to take snapshot at a much faster scale, okay, or you need to take the photographs of the apple which is falling by flashing the light at a very first scale, and then taking the image, and this is known as stroboscopy. Now, how fast you should be able to you should take the image, how will you know? So, that can be very easily calculated, because suppose an apple is falling, that what speed it is falling, okay, what is the distance between the stationary state and then when it reaches the ground, and how long it will take to fall down. So, if you want to take at different time scale, you can easily figure out how fast you should take, because you also know about the acceleration. So, you can essentially take a photograph like this, which is essentially the time sequence of the image of the falling apple. Now, let us consider a real chemical problem where you have a molecule, and let us start with a molecular model. So, suppose you have a methane molecule, and this essentially not a molecule, but you take it as a molecular model. Now, this molecules, real molecules, they rotate, they execute rotational motion, right. So, this molecular model also we can rotate, and if we can rotate it very fast, say for example 2600 rpm, how will it look like to you? You will not be able to differentiate between different atoms there. You will see something really fuzzy. You may not be able to understand that this is a molecular model having 4 balls and sticks. You won't be able to guess that. So, now suppose you have a definite diameter for this red balls, and then the distance between 2 successive balls is given, then you can actually calculate what should be the resolution of your light flash, so that you can take the image at a as if the molecular model is stationary. Okay. So, this is the image of the stationary model, and when you allow it to rotate, it appears like this. This is a real image of a rotating model. So, you can immediately figure out that this is totally fuzzy, right. You can't figure out whether there is a molecular model or there is something else. Now, if you can really come up with a short pulse light, okay, how short we can work it out, then you can actually freeze the motion, correct. So, if you flash it for a very short time scale and you can detect that. So, while it is rotating, it has its own speed, but if you can come up with a much similar speed of this flashing, then you can freeze this motion in space, and you see something like this. Okay. So, this was under room light, and this figure on your right is under a proper light pulse. So, this is exactly the experimental geometry one can think of, that this guy is making a rotational movement here, and the light is being sent to this guy, and then there is a blocker here, and the camera sitting here takes the picture. So, if this light pulse is fast enough, then or short enough, sorry, then you can freeze this motion and you can get an image like this. Okay. So, what is the time resolution that you will need? It is needed to be something like 150 microsecond. Okay. So, you need to be short. Now, this is about molecular model. What about a real molecule? Say if you take say methane essentially. So, this time scale that you would need to freeze the motion in space is approximately a picosecond. Okay. So, that is an ultra short pulse. So, how to get that ultra short pulse? We know about that. We can prepare a mode locked laser and we can get the short pulse, ultra short pulses, you know, picosecond and beyond. We can go up to femtosecond quite easily. Now, is it only about creation of a pulsed light source, ultra short pulse light source? No, we also need to synchronize this pulses with this molecular motion. Okay. So, one needs to do a proper arrangement of doing the experiment as was done by Ahmed Suhail, where you have one pulse which excites the molecule and then the second pulse probe that excited state. So, essentially if you are trying to figure out what happens between this CH3I and sodium. So, how the transition state, so you create that molecule in the excited state, so the transition state is created and then how it evolves with the time, you come with a second pulse. Now, this second pulse if you come at a delay, so essentially what I was drawing earlier, like you have a potential well, you are exciting it here, so you are creating the transition state that is slowly evolving. So, when it is here you come with the probe, then when it is here you come with another probe, another, you take the whole snapshot up the transition state as a function of time, and that is how you do that by choosing a proper time delay between the pump and probe. So, this is the pump probe setup that Ahmed Suhail actually used. So, you can use this pump probe technique involving ultra short pulse laser. You can really study a very ultra short chemical processes. It can be bond breaking, it can be bond making, it can be bond reorganization, this isomerization. Okay, it can be a change in the conformation. So, various things are possible to be studied. One can study all these different processes which happen in very short time scale, as short as picosecond or femtosecond level, and these are all now possible. All these studies are possible because I have pulse laser, not only pulse laser but pulse laser with ultra short time scale. So, I hope I could show you certain examples of lasers in spectroscopy and in general the effect, the application of this laser spectroscopy in understanding several chemical processes. So, this is the that is all for this particular lecture, and let us meet again in the next class. Thank you very much.